Okay, this is the solution to the second exam um, in the fall of 2020. Okay, so you're only supposed to do this problem if it requires a free body diagram. And the purpose of this was to make sure that you were paying attention when I was teaching you how to determine whether you need a free body or not. This is going to be important for the final exam, especially because all of the problems are going to be mixed up and you need to find out how to proceed. Okay, so the first question you ask is it a dead giveaway? In other words, am I asking you to calculate a force? And if you notice what's being asked is, oh, whoops, that's not what's asked. What's asked is what's the acceleration of the block? So no, it's not a dead giveaway. So what do? You count the degree of freedom. In this case, it has 1 degree of freedom. It has 1 degree of freedom. What that means is if I give you one double dot term, you can find any double dot term that you want. So if you look at this, the block has a speed and is increasing its speed at 2 feet per second squared. So you're given one double dot term. That means you can find any double dot term that you want, and you do not need a free body diagram. And so this does not need a free body. Don't do it. So you're not supposed to solve this one. Okay. Now for the second one, what I was kind of doing, and maybe I shouldn't have done this, but the second problem was exactly like the first. So I'm just trying to emphasize: are you just guessing or what? So anyway, but it turns out that about probably half the class, I guess, freaked out and thought, well, there's no way he'd do 2 of them in a row. And so you went ahead and did it. Okay. So what I did was if you attempted either 1 or 2, I assumed that, you just freaked out and you thought, well, I have to do 1 of them. So anyway, I went ahead, if you tried, I went ahead and graded based on what you tried to do. Okay. So what I'm going to do is, if you, for example, imagine that if you just imagine that I left this off, right? So just a very small change in the statement of the problem. Now all of a sudden you need a free body diagram. Why? Well, the reason you would need it is because it's 1 degree of freedom, but I haven't given you a 1 double dot term. So there you have to draw a free body. Okay. So let's say that's what you're going to do. You're going to use a free body diagram. So over here I have the free body. It has a weight down, which is the well, right here, 3. That's the weight, and it's vertically down. What other forces? Well, you look for contact. There's a pressure force right here coming from that blue circular thing. Because there's friction, you have a friction force right here, which is parallel to the surface, and it opposes the slip, right? It doesn't like slip. And so if this guy is slipping to the right, then the mu Kn goes back up to the left. This force right here, the Fs, that is the spring force, right? So the spring is touching it. So those are the forces that are acting on this. What do you do after you draw the free body diagram? You sum forces. In what direction? Well, whatever makes acceleration easy. Well, if you look at what's happening, it's on a circle, so you know the path. You are told speeds, right? Radius of curvatures, things like that. So I'm going to use tangent normal. So that's how I decided to use tangent normal. Okay, so now that you've decided what direction, you need to determine where the arrows are for tangent normal. Here's the arrow for tangent. Here's the arrow for the normal. I just moved it down a little bit to keep it away from the others. So the black arrows are the directions. They're not forces. They're the directions. So now all you have to do is sum the forces in the tangent direction. So the Fs are not in the tangent, right? There's none of those in there. The 3 has a piece of it. And if this angle here is theta, then this angle right here is also theta. So what you're looking for is this. Let me put it in blue. You're looking for this distance right here, that force right there. which is the sine. So it's 3, the weight, 3 times the sine of the angle theta. And then you also have, and it's pulling it into the nt, so that's why it's positive. Then you have mu kn, but it's backwards, and that's why it's a negative. And that equals the mass times the acceleration in the tangent direction, which is v dot. That's why you have to pretend like that wasn't given. If you want to solve it legitimately, you have to pretend like that's not given. Okay, so anyway, then you sum forces in the normal direction. So you have n, it's negative, right? It's negative n because it's pointed backwards from the normal direction. Then you have the spring force, and there's the spring force. Remember, a spring force is equal to the spring constant, which is 2, times the stretch in the spring. It's actually the deformation. So the spring is 2 feet long. The free length is 1 foot. So the stretch is 2 minus 1, or 1, times k. So that's 2 times 1 is the spring force. Let's see, this is the weight times the cosine, right? And he's positive because he's pulling in the normal. That equals mass times the normal acceleration. Okay, if you count the number of unknowns, you don't know n and you don't know v dot. So I've highlighted them here. So you have 2 unknowns and you have 2 black equations. So we're going to just solve it, right? So take the second black equation, solve for the normal force. Normal is equal to, well, you can see what it is. And you just punch it in, you get n equals 4.4. Now that you have n, you substitute it into the top black equation, and so you'll see it in red here, right? Because the normal force comes out as a positive number, it means, yeah, I got it right. It is, in fact, pushing the block out. That's how I know it's still in contact with the surface. So anyway, then you calculate the v dot, and you get 6.3. Now what it asks for is the acceleration. Okay, so either you give me the 2 numbers or you get the acceleration magnitude. But anyway, if you want the magnitude, then you just square the 2 and take the square root, 7.74. But again, like I said, it shouldn't have been done because it really didn't need a free body. But if you did, then I graded it as if it was a legitimate thing to be done. Okay. Okay, so for problem 3, this one says only do this if it does not need a free body diagram. Okay, so how do you know? Well, in this case, I want the speed. It's 2 degree of freedom. And so I have to tell you 2 things. And one is the speed of the top rack, right? And I also tell you that point A is fixed. So I'm giving you 2 velocities, 2 degrees of freedom. You don't need a free body diagram. Okay? All right, so how are you going to do this? Well, it's either ropes and pulleys, which that's ridiculous, right? Vector loop, and like in class I said, well, when things are rolling like this, it's really hard to figure out the loop or special points. So I'm going to do special points. Okay, now, how many special points are there? Well, I'm showing on the solution that I have A, it's special because I know something about it. Q, P is special because I want to know something about it. And then there's another special point down here. Call it, B or whatever you want to call it, but there's one at the bottom. So at most, there's 1, 2, 3, 4. So at most, you're going to write 3 equations. Now, what I'm hoping for is that I won't need to do all of those. So what I did was to use the special points. I'm using Q and C, right? And when I think about it, I go, the reason I'm using Q and, Q, oh, yeah, okay, I'm sorry. I'm going to use the simplified equations, right, that you had a homework set on. And there's 2 conditions to be able to use the simplified equations. 1, you have a point that's fixed. Aha, I've got A, it's fixed. 2, there can't be any row motions. So, all the special points on this blue gear, none of them have relative motions or relative velocities. And so I can use the simplified formula. So that's what I'm going to do over here in green. If you don't do the simplified formulas, then over here on the blue, I did the, if it wasn't simple, if you didn't recognize that you could use those. Okay, so anyway, Q, I'm using the contact for, it's Q is in temporary contact, no slip with C. So the table says that they have the same velocities. So C is moving 3 to the right, so it's 3I. So that's the velocity of Q also. Okay, so now this formula right here is the simplified formula for the gear in the points A and Q. Velocity of Q is equal to it's equal to the multiplication of the omega times the distance between them. So that's omega times 0.3. And then you have to get the direction, you have to look at it and see which way the thing is going. So if I think omega is going counterclockwise, right, that's what I always do. I think it's going counterclockwise. Well, if that's the case, then Q is going to be moving to the left. And that's what I do with that arrow. Okay, so now what I'm going to do is say, well, I know what Q is, right? It's up here in this formula, right? That's what the velocity of Q is. And this is what I think it is from the simplified formula. So I just equate them. I say, this is from the simplified formula. He's 0.3 W left. That's why he's negative, right? He's left because I think omega is counterclockwise, right? And I set that equal to what he really is up here, 3I. And then what you solve for is just omega. Omega ends up being a negative, which tells me no, the blue guy is going to be rotating clockwise, not counterclockwise. Well, you probably knew that, right? Okay, and so omega is clockwise, just like I show here. And the magnitude is 10, okay? Now, I want I think it's the speed, right? Determine the speed. Okay, I want the speed of P. Well, I'm going to use the simplified formula again. It's omega times the distance. So it's 10 times 0.3, 3. And then if you want the direction, you have to look at it and go, well, if this guy is going clockwise, oops, I made a mistake there. If he's going clockwise, then he's going this way. He's going up. Okay. But since you just wanted speed, then you have that one. Okay, if you want to do it without the simplified formulas, or if you didn't recognize they were, okay, then here's what I do. I write between Q and A. Why Q and A? Because I know something about Q. I know the number, and I know the number for A. And so it seems to me that this might be the best way to start. So I write velocity of Q equals A. So you recognize that. There is no relative motion. A is held fixed. And so then when you do your cross product, you find the same thing for the omega. It's a negative 10. And like usual, if I don't know the number omega, hey, he's going counterclockwise, okay? But I get the negative and it tells me, no, that's wrong. Okay, then what I'm looking for is I'm looking for the velocity of P. So I'm going to see if I can get that. Velocity of P equals A plus omega, but now I know omega, and if you notice I put in minus 10K, right? Because I know now that it's a negative. Cross, and then the R, it's 0.3, and it's left. When you go from A to P, it's left, so that's why it's a negative I. And then you do the cross product, and you end up with the same thing here. And yeah, so I'm not sure why I'm getting it going down, because it's obviously not going down, it's going up. Anyway, so I have a negative sign wrong in here somewhere. Oh, K cross I is a positive J, not a negative J. K cross I is J, positive J. So that's a negative, negative is a positive. So that was my mistake right there in the cross product. Okay. Let me pause here. Okay, for this one, again, you weren't to do it if it does not require free body diagram. So again, I'm just trying to get you to practice doing this because you're going to have to do it for the final. In this case, it's not a dead giveaway. I'm not asking for a force. So you count the degree of freedom. It's 1 degree of freedom. That means if I give you one velocity, one dot term, you can find any one dot term you want. And I do. I give you angular velocity. So that you do not need a free body diagram to do this. So we're just going to we're going to do it. Okay. Okay, so there's two ways you can do this. So when I graded it, I had a question number 4, which I think corresponded to people who did it with special points. And then I had a question number 5, which was graded as if, for those people that did it as a vector loop. Okay, so one of either 4 or 5, you should have a 0 on, because you did it one way or the other, and then I graded it based on the way that you did it. So in red, I'm doing special points, and so in blue, I did it with vector loops, just so you can see how to do it either way. Okay, so with special points, there's on this body, you've got A, you've got O, and you've got B. So you've got 3 special points. So at most, you're going to write 2 equations. I'm going to try to get this thing done with just 1 if I can. And so I'm going to focus on O and B. Now, the reason I'm going to focus on O and B is O I know something about. I always like to have those in my equation because there's fewer unknowns. And I include B because that's the point that I'm really most interested in. I want his velocity. So that's why I use B and O. So on the first equation up here, I write between B and O. And so you should recognize that as the standard thing. Now, the VREL is non-zero because B and O can change the distance between them. So there will be a VREL in this particular problem. Okay, so once I write that equation, then I plug in. What do you know about the point B? Well, he's moving horizontally. Which way is he going? Well, you can probably tell, right? But I say, I don't know the number. Okay, so then I put him in as just some number, a positive thing, and I say he's going to the right. And so if I'm correct, I'm going to get a positive number for little VB. Okay, what's the velocity of O? He's in permanent contact with the ground. He's 0. What's the omega? Well, the omega is given. It's 3, and it's counterclockwise. So it's 3, it's 3, and it's positive K, right? So that's the omega. The R from O to B is, and I'm just going to pick it off over here. If you're going from O to B, I'm going to go to the right a distance of X, and I'm going to go down a distance H. And so that's why it's plus, it's X plus I, because it's right, H minus J, because he's down. Okay. Now for the VREL, what you do is you pretend like you're standing on the slotted member. So you pretend like you're standing here, and you're looking at the O and the B. B is going to look like it's moving in that slot under your feet. Okay. I don't know whether he's coming towards O or away from O. So I just say, well, I think he's getting further away, because that's what I always do. So I write it as VREL. But then I say, okay, here is the direction of the slot. He has to be in the slot. He's got to be going a cosine of theta, right? So up here on the theta. So this slot is horizontally. Okay, I'm not exactly sure where I was on this one, but basically I think I was talking about the relative velocity and term. Okay, and then once you have that, then the next step is just to simply do your cross products, which is what I'm doing here. And then after you do cross products, you take all of the i's on the left and equal to the i's on the right, which is here, and all the j's on the left and j's on the right, which is there. And the number of things that are unknown is you don't know VB, you don't know VREL, and I don't know X. I do know H, that was given, but I don't know X. So I've got to find X. Now, what you want to do that we in class, these things right here are velocity equations. You don't ever solve a velocity equation for a double dot or a no dot term. So you do not look in these circled equations for X. You don't do it. You've got to find it some other way. Okay, so you look back at the picture, and this is how you'll find the relation between the H and the X. So the tangent of theta is equal to 3 over X. So then you can solve for X. Now that you have X, now you only have 2 unknowns, and you can solve for VREL and from the bottom equation, and then get the VB. So that's just algebra there. Okay. Now, for those of you that did it with vector loops, right? And you know, did you need all of the special points? No. So, you know, you didn't have to do them all. Okay, if you do vector loops, then over here what you would do is you know, I'm going to use a vector loop. I'm going to go from O to B to P, which I've drawn here, right there, back to O, right? So I'm just trying to keep it as simple as possible. Okay, so I'm not exactly sure where I left, but I think I was doing this vector loop. And so the vector loop that I'm going to go is I'm going to go from O to B to P to O. And, you know, so it's convenient and smooth things. Hang on. Okay, let's see if I can get through this now. So anyway, I showed you the loop that I'm going to use. So if you go from O to B, you stay on the mechanism as much as you can. So I'm going to go a distance L, which I don't know, so I just call it a variable L. But I know the direction is going to be cosine of theta, right. That's why it's positive, cosine theta. And then I'm going to go sine theta down, so that's why it's a negative. And now I'm standing at B. Then I'm going to get off of the mechanism. I'm going to go horizontally a distance x to the left. Left is negative. And so a distance x. And then I'm going to go back up, so it's positive, distance h. Okay. Now, if you want velocity, then what you do is you take a derivative, right? So I'm taking a derivative. The things that are variables are L is a variable, theta is a variable, x is a variable. Everything else is a constant. So when you take a derivative, the first term you have a product. So you have the derivative of the first term times the second term plus the first term times the derivative of the second term. Don't forget the chain rule. And then for the x, he's just got the one term, so that one's pretty simple. The h is a constant, j is a constant, so that's why it disappears. Then what you do is you pull off the i's equal to the i's, or in this case, I equals 0, j equals 0. So the i's are given by right here. Here are the i's. They equal 0, and here are the j's. How many unknowns do you have? You have L dot. By the way, that corresponds to the V dot, the V rel. The V rel and the L dot are the same thing. But anyway, so you have the L dot unknown, theta dot is known, and the X dot is unknown. You also have an unknown L, so you got to find the L. Now, these, the highlighted equations are dot equations. You don't solve for double dots from a dot equation. You don't solve for no dotted from a dot. So I'm not going to use these equations to solve for L. I've got to get L some other way. But, and so so I'm keeping that in mind. But, so then the bottom equation right here, I'm going to solve it for L dot, right? Because it's only got the one variable in it. So I solve for L dot, which is given here in red. And then I'm going to take the L dot, stick it into the top equation. And when you do, you can solve for the X dot. And the X dot is equal to this stuff here. So you just manipulate it around, and here's what you get. You end up with the VB equals the this term. Well, anyway, you can see what it is. And now the only thing that you need is you need to find out what L is. And again, you don't use this, the dotted equations for an undotted term. So what you can do is you can come up here and say, I need to find L. Well, L is equal to, or, a couple of ways I guess you could do it. How did I do it? Okay, L sine of 30. So L, hypotenuse, L sine of 30 is equal to the H. Right, so that's the formula that I used. L sine 30 equals H. H is 3, and so you can solve for L. Once you have the L, you stick it into the equation, and you end up with exactly the same numbers that you had using special points. You could, if you wanted to find the L, you could use the undotted vector loop equation, this one here, and you take i's equal to 0, j's equal to 0, and that'll get you formulas to calculate the the value of x and the value of L. So if it wasn't a triangle, for example, triangles, it's probably easier just to look at the triangle and use the law of sines, cosines, or whatever it is to get the relationships. But if it's a trapezoid or something weird shape, then you can use the vector loop equations to solve those, and it'll get you the positions. Okay, so I think that's the end of it, and I'll post this.